Welcome to Math 389. And so this is advanced analysis. And what we're going to do today is we're going to talk a little bit more about the Baker-Campbell-Hausdorf formula, and then talk a little bit about generalizations. We're going to talk a little bit about varying parameters. So as always, I'm trying to adjust the lectures based on what you tell me you're doing. I debated preparing a lecture in advance and having something nice and polished versus trying to do something by a seat of the pants. And I decided, not because I didn't have time, but it would be more fun to try to do it by seat of the pants, to just really talk about the thought process of how you do things. And that's my story, and I'm sticking with it. All right, so here is the Baker-Campbell-Hausdorf formula. It's beautiful. It's nice that there are numbers, and we've talked about how there might be some meaning behind these numbers. How would you show that this is true? How would you at least gain evidence that it might be true?
For example.
Yep. Put in some examples. Choose some x's and y's, and now try to calculate z. And then once you have those, calculate the matrix exponentials. Then multiply them on the left-hand side and compare them to the right. So maybe you can find some matrices where x and y don't commute, but maybe x commutes with the commutative of x and y commutes with the commutative of x and y. So is even that doable? So can you find two matrices x and y such that x commutes with the commutative of x and y, but x and y don't commute? So I'll leave that as something for you to think about. How would we calculate this? Well, we have to use the matrix formula, and we'd have to expand. So remember that e to the a is I plus a squared over 2 factorial plus a cubed over 3 factorial. So if we want to try to even show that this formula is reasonable, does everyone agree that it is a nightmare? Right? So here is a really nice trick. We can use epsilon 1, epsilon 2, we can use uv, we can use little x, little y. There's lots of ways of doing this. I'll change notation a little bit, and I'll consider e to the a, e to the b versus e to the c. This is a hard problem. So I'm going to multiply a by the scalar x, b by the scalar y, and I'll have some matrix that will depend on x and y. Think of x and y as small. Maybe epsilon 1 and epsilon 2. So if I start to look at the left-hand side, it's I plus ax plus a squared x squared over 2 factorial plus ... times I plus by plus b squared y squared over 2 factorial plus ... And now what do I get when I multiply things out? So the first term shouldn't be too bad. So what's the first term? I. What's the second term? Ax. What's the next term? By. Now, what's the next term? Ax, by. Anything else living with ax, by?
Third terms. Those. Well, a squared x squared.
Yeah, so maybe I'll have the 1/2 a squared x squared plus abxy plus 1/2 b squared y squared. And just put together all the terms of order 2. And now let's look at e to the c xy. That's going to be 1, I'm sorry, the identity plus c of xy plus c of xy squared over 2 factorial plus dot dot dot. What do you think c of xy should be? So what do you want c of xy to be?
Some kind of binomial.
Okay. So one possibility is maybe it starts off with ax plus by.
One over square root of 2.
I'm sorry?
1 over square root of 2. The coefficients.
Why would those be the coefficients? So if you think about it, when you expand things out, if c of xy is just ax plus by, then things are going to be very nice. But it's not going to work. It would work if a and b commuted. So there needs to be more terms. So the question is, are there more linear terms or are the terms of higher degree? If we look at this, it's got to equal I plus ax plus by. So it seems like when I'm expanding things out, this should be the only factors involving just x and y. Because if I look at this term, that's going to be squaring things. So if I have an x, it's going to be at least an x squared. If I have a y, it's going to be at least a y squared. Or I could have an x times a y, it'll be a xy. That cxy term cannot impact anything in the cxy. So I think it's got to be ax plus by, but there could be more stuff. Right? And I have to look at all the things that could be of order 2. So maybe I have some constant, maybe c2x m. And now the notation is going to become terrible. Maybe m2x x squared plus maybe c1 xy m2xy xy plus c. I'll call it c2. Sorry, c2y. Or maybe just c2xx c2yy m. Maybe instead of 2x, maybe better notation might be maybe xx. M y squared plus dot dot dot. And now if I start to expand things out, I would get I, and then I would get ax plus by plus, now if I want to get something of degree 2, I first get everything from the cxy. So I'm going to get all this crap over here. So I would get the c2xx mxx x squared plus c2xy mxy xy plus c2yy myy y squared. And those would be all of the degree 2 terms coming from the cxy piece. But I also have degree 2 terms coming from squaring c. And when I square c, how am I going to get a degree 2 term? It's going to be coming from the ax plus by. And so when I square that, I'm now going to get plus a squared x squared plus abxy plus baxy plus by squared. And so on and so on and so on, and the nightmare continues. What's the only way if I want this expression and this expression to be equal? What must be true? Or what do you hope is true? So when I look at the expressions, do they start off looking like they're the same? They both have the identity. That's great. Okay. Do they have the same linear terms? Can I make the quadratic, can I make the degree 2 terms equal? Can I find coefficients in matrices? And then do I have any freedom in what those matrices are? So if I want the x squared terms to be the same, is there going to be a way to choose this over here to make the x squared terms work out? Oh wait a minute. I have a typo over here in the green. I forgot that there was a 2 factorial. Oh no, this, right. So over here, this should be divided by 2, I think, in all of these. And the greens do not have it divided by 2 because they came from squaring the linear. So you said that C2XX has to be 0? Why does it have to be 0? Let me just make sure that this is recording. I think I said recording. Yes, it is recording. Good. So you want the x squared terms to be the same in the 2 places. So here, if I look at the x squared term, it's 1/2 a squared. Oh, okay. Oh, did I drop the 2? Okay, let's see. Oh, yes, they have it divided by 2. You're right. You are right. And then the red terms don't have the divided by 2. I put the divided by 2 in the wrong spot. Thank you. Okay, good. Okay, now that we have that, then yes, then the mxx. So either C2xx is 0 or the matrix is 0, right? We don't know that C2xx is 0. Because it could be that maybe I need it to be non-zero for something that's going to come in later. But if the matrix is 0, that's really the same as the coefficient is 0. So in some sense, do I really need these coefficients, or should I just absorb those coefficients into the matrices? Is there really any gain in putting in those coefficients? No. I'm sorry?
They always come with matrices.
Yeah. And so I could absorb the coefficient into the matrix. It's a question of which is going to be more useful. So why do you think I would write the coefficients like that? And again, it could be, Professor Miller's phoning it in, didn't prepare the class ahead of time. And, this is why you don't teach a 300 level class like that. Or maybe Professor Miller has decades of experience and this reminds him of other things he's seen, and that's why he's doing it like this. I know which answer I hope is true. So do you notice how we have really nice coefficients? And if you look at the expansion of Z, it has nice things involving the matrices X and Y. I wanted to write it like this because maybe these matrices will be nice things in terms of A and B, and these coefficients will be nice in terms of factorials. So in some sense, I'm writing it like this because I can potentially extract something nice. If I have a matrix that's non-zero, is it square non-zero? So could I give you a matrix A such that A is not the zero matrix, but A times A is the zero matrix? Yeah. So if I give you the matrix zero, if I give you the matrix 0, 1, 0, 0, you might remember the phrase nilpotent. It's a nilpotent matrix. You can easily see that all the eigenvalues of that matrix are 0. So eventually you're in trouble. So you've got to be careful. So we don't know that MXX is 0. We don't know C2XX is 0. We know the product is 0. And if we don't extract the C's, if we just call it some matrix, then we're fine. But we can definitely figure out what's going on with C2XX. What about C2YY? By symmetry, we can figure out what's going on here. And now we're left with the remaining piece. So for the remaining piece, is there a choice for that so that we would get BXXY? So, again, hopefully I haven't made any mistakes. We want, I think it was ABXY to equal, we're calling it C2XY M2XY XY, and then we had a BXY over 2 and BAXY over 2. So 1/2 AB plus BA XY. So we would need, we've got a lot of XYs. I can remove the XYs from both sides. And so I want to solve and get AB equals C2XY M2XY plus 1/2 AB plus BA. Hopefully it's clear to you what to do because I didn't prepare the lecture. What is it screaming at you to do right now? So I'm trying to solve for what?
Well, for the product.
What are we trying to find?
Well, both the coefficients.
Yeah, so we're trying to find this piece. How can we find that? What should we do? Yeah, move this over to the other side, right? Subtract. And notice it's going to be really nice because when we subtract, we get AB minus 1/2 AB. Well, that's just negative 1/2 AB. And the other is plus 1/2 AB. So we get minus 1/2 AB minus BA equals C2XY M2XY. Sorry, there's no minus sign on the, yes, you're right. There's no minus sign on the left-hand side. You're right. Thank you. So now, does anybody recognize the left-hand side? It's 1/2 the commutator. So there is 1/2 or 1/2 factorial, maybe. The commutator of A and B is C2XY M2XY. And so, boy, does this seem to suggest good choices for the matrix and the coefficient in front. And if you look at what was going on for the claimed formula, there it is. 1/2 the commutator is the next piece. I am tenured, so it doesn't really matter what I do. I could assign you to do the next term. How many of you have done complex analysis? So there's a beautiful result called the Schwartz-Christoffel formula, which talks about how you can map any simply connected open set to the unit disk. And in some cases, you can extend to be a map from the boundary to the boundary. And so I remember I was taking a graduate mathematical physics class, and they wanted us to write down the explicit map from like a pentagram to the unit disk, extending to the boundary. And I did the calculation of what my exam average was and what my homework average was and how much that one problem was worth, and decided not to do that one problem. It is the only problem in my undergraduate career that I chose not to do. The amount of times that would be required to do it was not worth it. Could I have done it? Of course. Yeah, it's just a painful brute force calculation. And I use this in the nicest possible way, and I mean the same thing about you. Could you calculate that the next term is 1/12 the commutative of x with the commutative of x and y minus 1/12? Yes. I have no doubt, especially given that I'm telling you this is what the answer is, that you can manipulate the expressions to get to that. We need a better way. And this way is not going to do a great job of showing how things are going to connect and just dealing with 2 sick kids at home right now. So this is hopefully enough to give you a sense that the problem can be done. That the problem can be done maybe at a high level, that there is some expansion. And the expansion should be functions, whether or not it's a nice function, we don't know. But there should be a way to do this. Just like we know from the fundamental theorem of algebra, I give you a polynomial of degree 5, it's got 5 roots. That doesn't mean I can write them down in terms of the coefficients. But once I give you the coefficients, it determines the roots. There should be a way to determine what the expansion is. And the idea we're using is the only way something like this can be true for all values of x and y is if the constant terms match, the degree 1 terms match, the degree 2 terms match, and so on and so on and so on. Is everybody comfortable with that? Or is that something that needs to be proved? Can I give you 2 different infinite polynomials that are not identical? And so, the hope is, let's say I give you, let's say f of x, y equals, it's going to have to be like a double sum, a n m x to the n, y to the m. And I'll give you g of x, y is the sum of b n m x to the n, y to the m. So this would be a00 plus a10x plus a01y plus dot dot dot. This would be b00 plus b10x plus b01y plus dot dot dot. What can you deduce? If, of course, these are equal. What can we deduce if they're equal?
Every coefficient, yeah.
How? So what coefficient can you get first?
A00, B00.
Yeah, how do you get the constant terms are the same? You plug in x and y equals 0. So f00 equals g00 implies a00 equals b00. So now let's look at, we'll call it maybe f00 of xy is f of xy minus a00, and g00 of xy is g of xy minus b00. And so this is where it's nice to be able to just do cut and paste. So there is the f. And so now we know these have to be equal. So now what can we do? So we could do derivative, but now you have to be able to justify taking derivatives. Fortunately, I've just passed out a book that, oh, except that's derivatives and integrals interchanging. But an integral is kind of like an infinite sum. So what can we do next? Good. Take y equals 0 and then factor out x. And then when you do that, that will then get you a10 equals b10. And then it's just shampoo mathematics. Lather, rinse, repeat, just keep arguing like this. Right? So one of the nice things is as you go higher and higher up in mathematics, you get to do fewer and fewer details. And you say, hey, and you wave your hand. You get really good at waving your hand. Stuff like this you might have seen in a probability class. In terms of looking at generating functions, is the generating function unique? Can two different distributions have the same generating function? And unfortunately, it is possible for two different probability distributions to have the same moments. It's horrible. It's absolutely horrible. And so if I give you a probability distribution, so f of x is a density if it is non-negative and it integrates to 1. And then the kth moment is the integral of x to the k times the density. And the hope is that if you know the moments, you know the distribution. It is not the case. If you take complex analysis, there's a beautiful theorem called the accumulation theorem, which says if you have two complex valued functions that agree on a sequence of points that converge to a common point, then they're identical. This is not true in real analysis. So real analysis is hard. The politically incorrect phrasing I like to use is real analysis is the democratic branch of mathematics, which lets every function in. It has very minimal bars. Yeah, come on in. Complex analysis is the exclusive country club of mathematics that is going to be sued for its restrictive policies of whom it lets in. It is incredibly restrictive to be complex differentiable. Being real differentiable, it's not a big deal. Complex differentiable is a lot. This is one of my favorite functions in all of mathematics. Do it properly. Let's do x cubed sine of 1 over x. Is this function differentiable? And is it differentiable maybe almost everywhere? Are there any places where you are not concerned about its differentiability? So 0 is the place where you're not concerned? Okay. So other than 0, do we agree that this is clearly differentiable? How would you prove it's differentiable at 0?
Is it squeeze?
So you could try the squeeze theorem. We know near the origin it's going to be bounded by x cubed. So I should probably define it as to be 0 at x equals 0. And then f prime of 0 would be the limit as h goes to 0 of h cubed sine of 1 over h minus 0 over h. And that limit will be 0. Because when h goes to 0, remember h is never equal to 0. So the sine of 1 over h makes sense. It's going to be between minus 1 and 1. The numerator is bounded by h cubed. This function is differentiable at 0. This function is not going to be twice differentiable at 0. Because when you differentiate the sign of 1 over x, you're going to get a 1 over x squared coming out. When you do it again, you're going to get a 1 over x to the fourth. Things are going to blow up. This function is differentiable once, but not twice. So in real analysis, you can have a function that's differentiable once, but not twice. In complex analysis, if you're differentiable once, you're differentiable infinitely often. In complex analysis, if you're differentiable, you equal your Taylor series expansion. Remember, in real analysis, we have, I think we've seen this horrible function or this wonderful function, depending on your point of view, e to the negative 1 over x squared, where we showed every derivative of this function is 0 at 0. So the Taylor series of g is identically 0, but g is not identically 0. Right? I'm not supposed to wax philosophical, so I guess I can't say that this should bother you. I'll just say it bothers me, it upsets me that you can have a situation where all the Taylor coefficients is 0, but the function is not identically 0. Right? You would love to have the Taylor coefficients uniquely determine the function. Similarly, we would love to have the moments uniquely determine the function. And so again, if people are looking for projects, there's some great results about two distributions that have the same integer moments. And they even have the same half integer moments, but they're not identical. And what's really lurking in the background is you can have this ridiculous stuff over here where I have this function which does not equal its Taylor series. Another way of looking at it is if I have a function that agrees with another function at a sequence of points, do they have to be identical? Well, what sequence of points? If the sequence of points is, say, the entire interval from -1 to 1, that's maybe that's a very strong condition. Do we have people here who gave a talk on something like this? With Dirichlet series? About functions, about regions, about looking at domains where functions were the same or could be different? I'm trying to remember your colloquium.
It was Fourier series.
It was Fourier series, wasn't it? Is, if I give you the Fourier series expansion of a function, when does that uniquely determine things? And if I remove just one point where they can be different, how bad is that? What if I remove a countable number of points? What if I remove certain types of uncountable points? And so over here, if I tell you two functions agree at the integers, but only at the integers, do the functions have to be the same? No. And so can somebody give me right now two functions that agree at the integers but are not the same?
4.
Okay, so if you take the floor function and what else? Okay, so the floor of x and x are the same at integers, but only there. So you have successfully answered the question, but I don't like your answer. Why don't I like his answer? The floor function is not continuous. So can you come up with a continuous function?
0 and sine pi x.
So 0 and sine pi x. That's good. Your example was fine, it worked, but this example, not only are they equal, but they're not, and not only are they continuous, but they're infinitely differentiable. But the integers are well separated. So can you have two functions agree on a sequence of points, say xn, which converge to 0, but not the same function? So I now want two functions that are different, and they agree on a sequence of points.
0 and sine pi over x, where the sequence of points is 1 over
So we could do, so sine, yeah. I'm going to not put in the pi just to. And I'm going to put in the x squared or the x cubed from earlier, so that if I then ask you, I want it to be differentiable, it will work. And so here's a way to have two functions that agree on a sequence of points that are differentiable, but they're not the same. This can't happen in complex analysis. So again, part of what I'm trying to do is just show you a little bit of what's out there. In complex analysis, if you have two functions that agree on a sequence of points that accumulate, then they must be the same function. Completely different than what's going on in the real setting. Okay. So when I tell you I have two functions that have the same moments, the moments are separated. If you had two functions, two probability distributions that agreed at a sequence of moments that accumulate, that converge, so they can't be integer moments now, but maybe moment 1.2, 1.02, 1.002, 1.0002, something like that, then that would be enough to force the distributions to be the same. So this is a big question, when do we have this kind of uniqueness? And in the stuff that we're doing here, we want to argue that these functions have to be the same, that we can just pick off the coefficients one at a time. We have to be careful because we don't necessarily know that we can differentiate, but we can set values of x and y to be 0. We can then pull out factors, and we can just keep iteratively going through like this. And so if these two functions are going to be the same, you can't have two different series expansions that are the same. So we would get that, if these two functions are the same, the only way this will work is we must have all the constants the same. Useful? Well, at the end of the day, we're trying to prove the Baker-Campbell-Hausdorf formula. We want to multiply e to the x and e to the y and get e to the z. I was looking at e to the ax and e to the by. What should I take x and y to be at the end of the day? If I take them to be 0, then I'll just get e to the identity times e to the identity. 1. When in doubt, your good answers are 0, 1, 1/2, infinity. Right? If I take x and y to be 1, I just get e to the a times e to the b. The way to see that formula is to introduce these extra parameters, x and y, that we don't, we only care about one value of x and y. We care about x equals y equals 1. So rather than solving that problem, it's actually easier to solve a more general problem with these free parameters x and y, and then at the end of the day, set x equal y equal 1. So this is a wonderful idea, that you want me to solve this hard problem? I'm going to solve infinitely many problems and then get your problem as a special case. That's what we're doing. It's a wonderful approach. So you put something in a family, you prove something about the family, and then you just extract that one special case. So it's just a lovely idea to be aware of. Okay, and so related to that, and this I think is taken from Professor Goldmarker's notes. Consider the following integral, and he has the remark, he defies the reader to evaluate this integral by the usual methods. What word do you fixate on when you hear that? Yeah, to me, there's two things. One is defy. What's the other word? Usual, yeah. What does he consider usual? I was applying for a job in the finance industry. I will not say much because this is being recorded, but I had a dispute with the interviewer as what was considered elementary. And so, my justification was, he didn't like my answer, and I gave him 3 different answers, and they were done while feeding my newborn son and holding a bottle. My feeling is, if I can do this while feeding a baby a bottle, this counts as it's not that bad. I'm not writing things down. This is not a hard calculation. So the question is, what is usual? I'll say anything that we can use, we'll call usual. We'll be friendly to ourselves. And so this is a challenge from our colleague. Any thoughts about how we could do this?
Put in a free parameter I for it, hit exactly wherever you use the Feynman trick.
Right. But that's not, so for that, that's not the usual method. And that's why these are the notes on the Feynman trick. But yes, and so the idea is to actually replace 2 with a parameter. I can think of 2 ways to attack this problem. So one is you could try x equals e to the u. As x goes from 0 to 1, what does u go from? Negative infinity. Right? When x is 0, u has to be negative infinity. When x is 1, 0. So then this would become the integral from negative infinity to 0. X squared is going to become e to the 2u minus 1, right? Over the log of e to the u is just u du. I will keep the minus infinity to 0, even though it kind of bothers me to be doing that, but that's not too bad. Any thoughts about what we should do next? Don't worry about whether or not it's legal. Are we worried about this integral being finite? So the first thing is, whenever you see an integral, you want to make sure, is this integral finite? As u goes to minus infinity, are things going to be okay?
Well, there are 2 halves, and the second half is 1 over u, 1 over u is good.
Yeah, 1 over u, I'm actually a little bit worried about that.
So we know that the first half should also be so that it cancels.
Right, and so as u goes to 0, what do we get? 1. So that looks finite, because that looks like 1 minus 1. So as u goes to minus infinity, the e to the 2u, I'm not really worried about that. That's going to be really small. But the negative 1, I don't like that. Does this original integral make sense? So as x goes to 1, the log of 1 is 0. That's blowing up. Now, I could write this integrand as follows. This is the integral from 0 to 1, 1 minus x, 1 plus x. And I can write this as the log of 1 minus 1 minus x dx. And so if I let t be 1 minus x, x goes from 0 to 1, t then goes from 1 to 0. This would be something like the integral from 1 to 0. 1 minus x becomes t. And then x plus 1 x plus 1 would be, I think, 2 minus t. And I would have the log of 1 minus t dt. So something like that. So there's a couple of ways of looking at things. I'm just trying to get a sense of what's going on as x goes near 1. Because the problem is, as x goes near 1, the top is blowing up. I can expand the log of 1 minus t. That's going to look like, t It's gonna look like, I'm sorry, minus t squared over 2 minus t cubed over 3. I've got a t upstairs. All right, so this is gonna look like minus 1. So near t equals 0, everything is fine. So I'm just doing this because I know the Taylor series near t equals 0. And so t being 0 is close to x, is the same as x being close to 1. So I think everything is fine near 1. That the problems with the log of 1 being 0 in the denominator is not so bad compared to the numerator, which does have a factor of 1 minus x or x minus 1. But what about as x gets closer and closer and closer to 0?
Basically the same as the integral though.
Yeah. And so do we have to worry about things blowing up? So again, your first thought whenever you see an integral should be, is this well defined? And I can use the log of 1 minus t is negative t minus t squared over 2 minus t cubed over 3 minus dot 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 to show me that near t equals 1, or so near t equals 0, everything is fine. When we do our conversion, so do you think this integral is well defined, or do you think I might have made a mistake somewhere? I did slip something by you. I started by being really good. I said, this is what x is, and x goes from 0 to 1, u goes from minus infinity to 0. There's one other thing I should have written. Yes. What does dx go to? E to the u du. And so we actually need an e to the u over here. This is one of the most common mistakes people make when they do change of variables, is they forget little factors like this. You should always check and see, no, wait, but it looks like that integral is well defined. This integral is not well defined. And that allowed me to know we must have made a mistake somewhere. Where was the mistake? Okay, it took a little while to figure it out, but the more time you spend writing everything down, the less likely you are to make a mistake. Okay, so now we are left with, can we integrate? Can you do the integral from minus infinity to infinity, or to 0, of e to the 2u minus 1 over u times e to the u? Well, I can write that like this. And that integral is not going to be too bad to do. It's at least clear that this integral is going to be finite. Any thoughts on how you could actually evaluate that integral? I mean, you don't want Professor Goldmacher to win, do you? Says it can't be done. Okay, so so you could try to do it by parts. So the problem is if you try to integrate by parts, you've got a 1 over u. If you take the derivative of that,
It's gonna be worse.
it's going to be worse. And if you integrate that, then you're going to get a logarithm. Well, maybe that's not so bad. Maybe you can handle the log of u times exponentials. So I'll leave that as one possibility. See if you can make that work. I would definitely say that falls under the usual methods. What else could we do? Do you agree that each one of the integrals now is fine? I can split up the two integrals. How could you handle the integral of, let's say, e to the au over u from minus infinity to 0? What might you want to do? It's okay if it doesn't work. You've got an exponential function. What might you want to do to it? Taylor expand it, right? This would be the same as the sum and goes from 0 to infinity, the integral from minus infinity to 0 of au to the n over u times n factorial. Well, you know what? Let's just make that an n minus 1 and put an n factorial there. Is that okay? What's the problem with this? Yeah, but I've got Cookie Monster here today, and he's giving me permission. So, am I allowed to interchange the integral and the sum? What can you tell me about each of those integrals? What can you tell me about their values? You're integrating u to the n minus 1 from minus infinity to 0. What are you going to get? Okay. Instead of undefined, what would you say? What's the value? Let's take n equals 4. So we're integrating u cubed from minus infinity to infinity. What do you get when you integrate u cubed from minus infinity to 0? Infinity. And notice the infinities are going to alternate being plus and minus infinity. So we're going to get an expansion, right? Now, we could play more games. We could replace the 0 maybe with an epsilon, and then take the limit as epsilon goes to 0. And then that would replace the infinities here with, like the natural log of epsilon. And then all these integrals would be finite. We have the n factorial, that's plenty of convergence. So maybe you could try to play some games like this. I'm trying to justify his challenge. Okay. When you try to do the standard stuff, this is hard. We could try to play some, nice games and whatnot, but it's not easy. Maybe you could do something with this log of 1 minus t and changing things, but it doesn't look good. So the Feynman integral trick is to, instead of integrating x squared minus 1 over log x, integrate x to the t minus 1 over log x. And then at the end of the day, take t equals 2. Now, the idea is, let's take the derivative. So if we want to take the derivative, that's d by dt of the integral from 0 to 1 of x to the t minus 1 over log of x dx. And now, what's the derivative of the integral? What's true about the derivative of an integral, at least for us today? It's the integral of the derivative, of course. So the Feynman method, you've got to justify this. So you can replace t with t plus h, subtract t, divide by h, put the integrands together. You're only integrating from 0 to 1. That's a compact set. So you can justify this. What's the derivative with respect to t of this? And how can I write x to the t? Because I want to differentiate with respect to the exponent. So how should I write x to the t? Yeah, it's e to the t log x. So the derivative of x to the t is just the log of x times x to the t. So we get g prime of t is the integral from 0 to 1. The derivative, well, the negative 1, its derivative is 0. The log of x is just a constant with respect to t. The derivative of x to the t is log of x times x to the t. So we just have the integral of x to the t dt. Oh, sorry, dx. All right. This is not a bad integral to do, right? This is just going to be x to the t plus 1 over t plus 1, evaluated 0 and 1. So when x equals 1, we just get 1 over t plus 1. When x equals 0, we just get 0. So we have g prime of t is 1 over t plus 1. So what is g of t? It's the integral from 0 to t of g prime of, let's say, tau d tau. This will just be g of t minus g of 0. So the question is, do we want, is this what we want? The constant term always gets a little bit annoying. So can we integrate from 0 to 1 g prime of tau d tau? This is the integral from 0 to 1 over tau plus 1 d tau. So what function has derivative 1 over tau plus 1? Log of what? Tau plus 1. We evaluate that at 0 and 1. Oh, sorry, we're integrating up to t, not 1, sorry. So we get the log of t plus 1 minus the log of 1, which is just 0. So you just get the log of t plus 1. When t equals 0, we do get g of 0 equals 0. So everything seems to be good. So g of t is the log of t plus 1. So g of 2 is the log of 3. So if I've done the calculations correctly, we have evaluated that integral. This is just absurd. That, again, you should not be in this class unless you are seriously considering math as a career or something allied with math. The goal is to teach you. I'm somewhat generous in terms of what I consider allied with mathematics. I actually found common ground with engineers and probability today. So I really want to emphasize ways to think about problems. This idea of having free parameters is wonderful. And sometimes the way you solve a problem is you embed it in a larger class where you can do something with that larger class. And then what you want is just actually a special case. How many of you have seen the gamma function to generalize the factorial function? So you can prove a lot of results about the factorial function by proving things about the gamma function, which now, because it's a function that is differentiable and it has a continuous input, in fact, you can even take it to have a complex input, you now have analysis at your disposal. Where are the inputs of the factorial function? Where do they live? Just integers. You can't do calculus with functions that are defined on the integers. I'm going to take the limit as h goes to 0 of f of x plus h, where x is an integer and my function is only defined on integers. Can't do it, right? You lose everything from calculus. But if we can somehow extend the factorial function to a new function that agrees with it, we can now use the tools of analysis. And so this is what we're doing here. And to some extent, this was inspired by people telling me what they were interested in and by the Baker-Campbell-Hausdorf formula, where to me, the best way to look at this, and best way doesn't mean I'm going to get a nice answer, but I'm going to know in principle, I could get an answer if I cared enough. Or if I had enough students who really needed, extra credit, right? You can grind through this. You might have seen calculations like this in probability where you have convolutions and you're trying to match things, and you might have seen this in differential equations and sequences, solving by stuff like that. This is a general idea, just brute force it. And they have to agree term by term by term. And we introduce these extra parameters. And then at the end of the day, we take x equals y equals 1, and that gives us the Baker-Campbell-Hausdorf formula. And so we saw the Feynman trick over here. Okay. And so, I've listed some other ones. In a book I wrote, I actually did x to the 5 minus 1, very different than what Professor Goldmacher did. And I used alpha rather than t, so completely different approach, right? And then I just listed above, I found these on a nice handout online. And so I just listed a bunch of other things to look at. So as an exercise, try to evaluate those integrals. There's a little bit of an art in terms of trying to figure out what is the parameter. Well, over here, since I'm writing things in terms of alpha, I'm being kind, right? And there, it's not going to be that hard to figure out how do I put something in terms of a free parameter alpha. I'm giving it to you that way. The hard part is when you have something like this, recognizing that the 5 should become the alpha. Hopefully, there aren't that many possibilities. And you just try a bunch of things. If you're integrating by parts and it's not working out, what should you do? Do it the other way, right? And so, a lot of times if I'm integrating by parts, maybe I have, x cosine of x dx. And I could try, u equals cosine x dv equals x dx. And then I'll get v is, 1/2 x squared. And I see that this was a really stupid idea. And so it's such a stupid idea. Let's get rid of it. And let's try the other way. And if we try it the other way, if we let u equal x and dv equals cosine x dx, then we get du equals good. The degree has gotten smaller. Things are nice and good. So a lot of times when there aren't that many opportunities, there aren't many things to try. Try one. If it doesn't work, try something else. This is, as I said, where computers will beat us because they can just try so many things. If I give you something more complicated, it may be the integral of x squared e to the minus x squared dx. How might you do things? What should you try for u? What should you try for dv?
Well, we want dx, x squared dx to be du.
So you could try, you want x squared to be, what did you want again?
Oh, sorry, maybe I was doing, no. I was thinking of substitution. I was thinking of by parts.
So there's 2 natural choices. What's one natural choice for you? X squared. The problem then is dv is e to the negative x squared dx, and there's no nice antiderivative of that. So bad choice. All right, what else can we do? So we could do e to the negative x squared, and then we would put an x squared dx over here, and then that will be nice, then that will give us an x. And the du is going to be a negative 2, oh my God. Maybe things will work out, but what's the concern here?
Sorry, why did we lose the degree of x?
Oh, sorry. You're right, sorry. dv was x squared, sorry. This should be x cubed over 3. Sorry. And so when it goes together, now we have something like x to the 4th. Even worse. There is another option. Yeah, we could try u equals x, and dv is e to the negative x squared x dx. And now there's a nice antiderivative with some constant that I don't care about. And then du is just dx. And that will be doable. So sometimes you have to work a little bit to see how do you group it. And the more factors you have, unfortunately, the more possibilities. But there's only going to be hopefully finitely many unless you multiply by 1 in a clever way. And now there's infinitely many possibilities. And that's why math can get very challenging. So it's trying to figure out how can you put this in a nice way. Has everybody seen how to evaluate the integral from minus infinity to infinity of e to the negative x squared dx? Everyone has seen this? So I can do very quickly. This is I squared is the double integral minus infinities e to the negative x squared dx, e to the negative y squared dy. Everybody's seen polar coordinates, then that we write this as e to the negative r squared r dr d theta. R goes from 0 to infinity, theta goes from 0 to 2 pi. And this we can do. And when the dust settles, we get 2 pi. And so then we get that the integral, because it has to be non-negative, is the square root of 2 pi. And this is the key normalization. If I give you, let's call it I of sigma, is the integral from minus infinity to infinity of e to the negative x squared over, has everybody seen the Gaussian? All right, so I'm going to just change things a little bit. I'll put in the factor of 2 here to make things a little bit nicer. Trying to think. Oh, actually, there might not be, I think there's no 2 here. I think the way things are normalized, it's just pi, not 2 pi. Who knows what this integral equals?
1 over 2 pi.
So if I put a 1 over square root of 2 pi sigma squared, it would be a probability distribution that would integrate to 1. So since I don't have this, this should just be the square root of 2 pi times sigma. What's I prime of sigma? If I can pull the derivative inside the integral, what do I get if I take the derivative with respect to sigma? So I have e to the negative x squared over 2 sigma to the minus 2. So I'll get a minus 2 sigma to the minus 3. So I will get, the minuses will reinforce, I'll get x squared over 2 sigma cubed e to the negative x squared over 2 sigma squared equals the square root of 2 pi. Take the derivative with respect to sigma and I get just 1. Therefore, the integral from minus infinity to infinity of x squared e to the negative x squared over 2 sigma squared is 2 pi square roots times 2 sigma cubed. So this is very similar to the Feynman trick. The way I can find this integral is I understand the integral for all sigma, And then I can just take sigma equals 1, and I have the integral of x squared e to the negative x squared. So this trick of introducing free parameters, there's a lot we can talk about this. But it comes down to, at the end of the day, we need to be able to justify these interchanges. So if somebody's looking for a good, advanced topic, if you've never seen justifying switching the order of a derivative and an integral, that is extremely valuable. Because when we're doing the Feynman trick, like all good physicists, we just manipulate the mathematics. The good physicists only do this in places where it can be made rigorous. But at the beginning, we don't know that we can just switch. So we have 2 minutes left. So with the 2 minutes left, I will just do the following. Let's let Fn of x be defined as follows. Here's 2 over n, here's 1 over n, here's 3 over n. This is one of my favorite examples. And I'm going to have it go up to height n. Okay. What is the integral from 0 to infinity of Fn of x dx? 1. Right? Just a triangle. What's the limit as n goes to infinity of Fn of x? So no matter what point I give you, it's always 0. If x is 0, it's clear that it's 0. If x is not 0, choose n so large that 3 over n is less than x. So note the limit of the integral of Fn does not equal the integral of the limit of Fn. So this is one of the fastest examples I can give, because we only had 2 minutes, of why you have to be careful in interchanging operations. And this function exists on the interval 0, 1. The problem is the function is getting larger and larger and larger as I look at these sequence fn's. It's not uniformly bounded. So as a general rule, whenever you see an infinity, you need to be careful, you need to be concerned about what's going on. And so, all right, so this is a good place to stop for today. We will continue on Tuesday. Keep sending me what you're interested in seeing so I can adjust the lectures accordingly.